and we will pivot now to the topic around legacy systems and turn it over to James.
Thank you very much. Sound working okay? Good. All right. So I am James Ivers, and I'm here to tell you about a new research project we kicked off this year called Untangling the Knot. And the big takeaway, the big thing to focus on is what we're doing in this project is we're applying an application of artificial intelligence for software engineering, by which what we're doing is we're using AI techniques to rapidly increase the pace with which we can make certain structural changes to existing software code bases. Now, so why that's important, well, we've seen again and again in research, literature, experience, that the structure of software has a tremendous impact on how difficult it is to change the software. And there's lots of things that we want to do to innovate, to get new capabilities to the field that involve making software changes, inserting new technologies, porting to new platforms. And the structure of software can have a big impact, positive or negative, in how difficult that is and how quickly you can do that. So a recent anecdote of the not so generous kind from a DoD program we were working with is they wanted to take a mission capability and move it from one platform to another. Logically, this sounds like a very simple thing. So they asked their contractor, how hard is that going to be? What do we have to do? And the contractor comes back with an initial estimate. It's going to be 14,000 development hours just to extract it from where it is right now. That's not time for integration and test. That's not time to put it in a new context. That's just to decouple it from where it is to begin with. And that's sort of the preparatory activity that you need to do to accomplish things that are really important, what you really want to accomplish. And so what we see is that this is an example of a common class of problems. There's lots of things you want to do with software once it's already in the field that involve restructuring it in ways like this. For example, if you want to take a big monolithic system, chop it into services, and put it into the cloud or federated architecture, you have to go through a bunch of these isolation exercises. If you want to take an existing piece of code and replace it with something better, something that performs better or has less reliance on proprietary code, in all of these cases, you have to start by isolating some important chunk of software functionality from the context it's in. And so what we want to do is to bring in AI for software engineering to do this in significantly less time. We want to do that in less than a third of the time that it takes to do everything manually. And so to understand why we think we can do this, we have to take a look at why does it take so long. And this lovely piece of modern art on the left gives you an example. This is a graph representation of a modest piece of software, only about 70,000 lines of code. But to represent the important structural elements like classes and interfaces and methods and the relations among them, you need a graph of about 10,000 nodes and about 50,000 edges. That's a lot of complexity for a development team to go through and figure out how to find where am I, what do I need to do, how do I go about making the kinds of changes that we're talking about. And so this is what we're trying to do in a much smarter way. Now we start with a technique popularized about 2 decades ago by Martin Fowler called refactoring. Refactoring is common in the vernacular of engineers today, and it's essentially a technique for making a semantics-preserving change to software. That is, the behavior of the software doesn't change, but the structure does in ways that makes it more maintainable, more portable, something of this sort. But unfortunately, even 2 decades later, while there's lots of catalog knowledge in terms of books about refactoring, catalogs of dozens of refactoring, it's still a very manually intensive process. Developers have to go through that big tangle of dependencies to figure out where they want to make a change. They got to rifle through the book to figure out which of the number of refactorings they want to apply. Then they got to go into the source code and multiple files and make all of those changes. And there's a little bit of tool support to help with this, but it's really only in the last step. All the intellectual activity to figure out what I need to do is done by humans. And that takes a tremendous amount of time. So we want to create, and are in the process actually of creating, an automated refactoring assistant that automates work in each of these categories of labor-intensive activities. There's a couple of key insights. One is that it's a semi-automated approach. We can't solve the whole problem, but if we can solve 80 or 90% of the problem, we can get those dramatic time savings in terms of making the changes in the first place. It also means that we need to take advantage of what developers know to point us in the right direction. Developers know what the capability is they're trying to harvest, so let's use that knowledge to feed an optimization algorithm to generate solutions to these kinds of problems. Now, if I put this in the context of that earlier example, that 14,000 hours would be less than 5,000. And that's a big savings at one point in time. But one of the things that we see is over the lifespan of successful systems, this kind of change needs to happen again and again as you introduce new technologies and go to new platforms, because software is always changing. So this isn't a one-time thing for a program. But an even more dramatic example is if you take a legacy monolithic system. And you say, I want to break this up into a service-oriented architecture. You're taking one giant piece of code and isolating it to a couple of dozen different services. that means you're doing this isolation activity dozens of times, which further calls for a need to automate as much of this as we can so that we can focus developers on the hard stuff. So the foundational concept that we're building on to make this a reality is based on recent research in search-based software engineering. Search-based software engineering is a field in which software engineering problems are reframed as optimization problems so that genetic algorithms and other search techniques can be turned loose to find interesting and successful solutions in practice. And there is some success in this space in doing this for refactoring. Current research is focused on a different notion of refactoring, solving a different problem than what we're looking at. Specifically, what they try to do is for a large code base, make a suite of changes across the whole code base to improve code quality metrics like coupling and cohesion and things like this. These tend to be global changes that don't necessarily accomplish a specific targeted goal. In our work, we're taking the inspiration and the success in that work, and we're focusing on a very specific goal. That is, given a problem, I want to isolate this piece of software. Now go find me a solution that I pointed you in the right direction. Okay? So if we step back and think about how we want this to work when we're done, the black box picture is we have this automated tool in the middle based on a search algorithm. As inputs, it takes two important things. It takes a code base, and here we're talking 500,000 million lines of code. We're not talking small things. And it takes a project-specific goal, by which I mean I want to harvest this piece of code for use somewhere else. I want to replace this piece of capability with something else. With those things as a starting point, we can turn search loose and in an automated fashion generate a solution. And a solution in this sense really means a sequence of refactorings, which may be dozens or hundreds of refactorings long that collectively accomplish the goal that the user is trying to get us to solve. Once we have that sequence of refactorings, we can then automate their application to source code to generate refactored source code out the other side. Okay, so that's the big picture, that's the end goal we have in mind. To understand a little bit about how this works, search algorithms used in this way have three key elements that are important. One is a representation of the thing that you're trying to change. That's the source code, some representation of source code. Second is operations that make some change to the thing that you're trying to improve. And the third thing is some way to measure the goodness of a change. This change is better than that change, and this is leading me towards a solution. In our case, we tweak those just a little bit. Our representation is going to be a graph representation of the kind that I showed you earlier. Our operations are going to be formalizations of refactorings that we can apply algorithmically. And fitness functions, well, these are the measures of success. In our case, this is an interesting topic in and of itself that I will come back to a little bit later, because it's not always that simple. So now we take a key insight. How do we actually take this problem of isolating source code, and how do we frame that as an optimization problem? Well, we start with the realization that not all dependencies in a graph are created equal for a given purpose. In this graph, this is the same graph as earlier, we've applied some semantic knowledge to recognize different differences. So for instance, if the code that we're trying to harvest for use in another context is in the upper left, you'll notice that some of the lines in this graph are red and the rest are not. So what this reflects is that not all dependencies really get in the way of what you're trying to accomplish. In that graph of 50,000 edges, maybe only a few hundred of them are really a problem. And so to understand what that means, if I'm taking a big collection of code and moving it to a new location, I don't really care about the dependencies within the code that's moving. That's all going to the same place. I don't need to touch it. I don't care about the dependencies among the code that's not moving. What I really care about are the dependencies from the code that is going to a new location to the code that isn't. Those are the things that will break if I don't find some solution. So this is a really important insight because this is something that we can algorithmically find very objectively. We can count the red lines in a graph. And if we make changes to a graph, we can say that a graph with fewer red lines is better because there are fewer problems that need to be solved. So that kind of an objective basis is the foundation for using a search algorithm to find an optimization of a measure of merit. What's really interesting, this also gives us a really significant scalability benefit. It wasn't the going in thing, but it's really, really important when we're dealing with large code bases. Instead of the existing refactoring work, search-based refactoring work, that looks at the entire graph and tries to make changes anywhere and everywhere to achieve some better state, we can focus only on the red lines. We don't have to care about 50,000 edges. We want to focus on those few hundred that are really a problem. And so in terms of scaling the exploration of large combinations of different changes we make to the graph, this is a tremendous advantage by cutting, in what we've seen so far in our data, 1 to 4 orders of magnitude of the things that we have to consider in our search space. And that's really important. Now, these red lines, I think it was Bill who said earlier, we like to name things at the SER. We're not good at it. Well, this is ours. We call the red lines problematic couplings. These are the things that get in the way. And one of the early things that we did in this project is we built a prototype to count these things for different scenarios. And so the chart here goes through 6 different open source case studies and 14 different scenarios we've defined to show kind of what problematic couplings look like in the field in a couple of ways. I'll focus first on the total column there on the right. There's a huge variation in the scenarios we want to accomplish in terms of how hard they are to accomplish. If we take a look at the first 4 rows, which are all a common code base, we see that we go anywhere from a few dozen problematic couplings to more than 13,000. 13,000 clearly is in the realm of automation. This is not something that you want your development teams quitting over. So one of the really clear benefits that we got early on is the prototype that we have right now can do this analysis on a code base. That given a scenario, this is the code that I want to move somewhere else, or this is the code I want to replace with something else. We can do the analysis to count these problematic couplings and give you some basis for estimating how hard that really should be. Right. The other thing that's of interest here is the columns in the middle. So as part of this research, we're really trying to drive ourselves from the data perspective, from the real world occurrences of these kinds of problematic couplings and the challenges that they come with. We're not trying to look at academically what is an interesting sort of problem to solve. We categorize the data in lots of different ways. This is just one slice to see what kind of problematic couplings exist in the field. And in this case, we've sliced it by the relation type. Is it reading a method, or reading a variable or calling a method or something like that? And so we're using this internally to drive the research. So, as I said, calculating problematic couplings is really important because it's what allows us to measure one solution as being better than another. To do so, we do this over a graph. And the schema on the left here is going to be familiar to anyone who's used modern OO languages. The things that are in it are the things you would expect. Entities and nodes are things like classes and interfaces and methods. The relations are reads and calls, type declaration and inheritance. Very familiar concepts because these are the things that as developers we can change in our program structure. And they're the things that introduce couplings between different things. So the nature of this, the kind of information we're representing isn't much of a surprise. To the right, we've got a few examples. The modest one that I talked about earlier and a more significant one, about 750,000 lines of code that we're working with right now. And the scale is that one moves more towards the 100K line for nodes and about 600K relations. But we're challenging ourselves as we do this research to work with big case studies from the beginning. So given this kind of a graph, what does it mean to change the graph? Here's where we talk about refactoring. For those who aren't familiar with refactoring, refactorings are operations that involve moving code from one place to another, or introducing new structural intermediaries like interfaces, or extracting subsets of code into a new entity to decouple some relations. These are the kinds of things that we're using. And we're using them first, not so much in changing the source code, but in changing the graph to measure the effectiveness of a proposed change. So in the first year, we did some initial set of about half a dozen refactorings, all from the move family. And we formalized each of these first in terms of preconditions and graph transformations. And then we progressed to actually making changes to the graph so that we can measure the effectiveness of each change. The encouraging note here is that with only half a dozen, we have an at least workable solution to about 3/4 of the problematic couplings that we've observed in these case studies. And more importantly, for about 14%, we've got more than one solution to each problematic coupling. And this is really important to the effectiveness of search, and what we're going to be focusing on as we move into years 2 and 3 is really fleshing out the set of options that can be applied, because the power of search is in exploring many more combinations than a developer can think through manually. And so having more options means better exploration of the space and better solutions coming out the other side. So now I want to come back to fitness functions. Success is a really key criteria, because if we're algorithmically picking a sequence of refactorings that get us to a better state, how do we characterize a better state? So I started with the inspiration that if we reduce the number of problematic couplings, there's fewer problems left to solve. That is a single fitness function, and by itself, it leads us to some really, really bad solutions. So a degenerate case is if I really want to minimize the number of problematic couplings, just take the whole system with you instead of the little piece of code that you're actually thinking about. It's not a very useful solution. And that's not surprising to us as architects and software developers, but we really need to reason about trade-offs. There are multiple criteria that come into play. And so here, we guide ourselves by the intuition, the reality probably, that if developers won't accept the solution, they're not going to use it. So in order to be effective, we have to think about a range of fitness functions that examine different criteria for success. Certainly, resolving the core problem and minimizing couplings is one of them that almost certainly will stick around. But there are other things that we want to do, like reduce the amount of work that developers have to do to realize a solution. And so just to give an idea of what that means, the more code that I touch, the more code I have to reinspect, retest, possibly recertify. And so minimizing how much code I touch can be really important to success. We also want to do things to make sure that the code is understandable after we made changes, that semantic coherence makes sense. When we move something, we move it to a place that makes sense, and the developer is not going to be surprised by that. So where we are today, we're really just working with the first two, again, interim steps. We're already finding some interesting results as we incorporate those into search. So in the first year, as we're bringing all this infrastructure together, the range of refactorings, the representation, the fitness functions, we've started with local search, which is basically a hill climbing algorithm. It's subject to local minima, local maxima, but that's okay. It gets us moving forward, and it's showing promising results. So this is a little difficult to read, but the 3 lines here show the application of the same search algorithm as guided by 3 different fitness functions. And the core measure in this first chart is the vertical is how many problematic couplings are left as you, moving across the horizontal, add more and more refactorings to the solution that you're considering. You see in each of these 3 cases, they perform pretty similarly. They're all going from about 450 to less than 100. That's a substantial improvement. But when we take a look at these same 3 runs against a different dimension, how much code are they taking to a new location? Here we see more variation. Now, this isn't surprising, but it is really encouraging because it shows the kinds of things that we can objectively measure in the graph do point to substantially different solutions and different acceptance by developers. And so this is something that's really helpful to us. Now, where we are right now, we've got infrastructure in place. We can generate recommended refactorings to solve a problem, but we wouldn't recommend putting those into practice just yet. We need more refactorings. We need more fitness functions. We need more studies with developers to what's really acceptable. We think in 2 years we'll be able to pilot this with organizations to tackle real problems and to have some confidence in the solutions the tool is generating. But even where we are right now, we can pilot the ability to solve problems. So if an organization has a portfolio of proposed changes they're making, we can compare the relative complexity of all these changes and give a lay of the land. So I'd like to wrap up by talking a little about why we're so excited about this. One of the key things is the observation that this is a really common problem. It manifests in different ways, whether it's services or platform rehosting or whatnot. But there's a common tendency that we know for successful software systems. Their lifespan isn't measured in months or years, it's decades. And over decades, there are a lot of code changes that happen, thousands and thousands of commits. And all of these changes have the potential to change the structure of the software in ways that can make future changes harder. Similarly, what we want a system to accomplish isn't stable either. We always have new requirements, we're integrating with new systems, we're trying to host in new environments. And unfortunately, okay, that's better. So unfortunately, there's a common trend. It's a lot easier for these 2 things to drift apart than it is for them to come together. It's almost like an entropic effect. The structure that you have and the structure that you want don't align nearly as well as you like. And if that gap gets large enough, we often start thinking of a system differently. We start thinking of it as a legacy system where it's just too hard to do anything. And so what this project is this is effectively an intervention. How can we greatly increase the speed with which we can produce a significant improvement in the structure, bring it much closer into alignment with what we want it to be in the first place? But it's really just the start of things because there's another project starting this month that you'll have to come back and hear more about next year that talks about how do we keep things in alignment in the first place? How do we keep those gaps from emerging? And a couple of cool things about this is these are almost inevitable problems for long-lived systems. This has wide applicability. These are good applications of different AI techniques to solve the characteristics of different problems. So for example, search is good at finding refactorings, but to automate design conformance, we need to use machine learning classifiers to recognize the design in as-implemented systems so that we can develop conformance checkers as part of our DevOps pipelines to stop developers from drifting too far from where they want to be. So collectively, there's tremendous value to programs, but there's also tremendous learning for us about the applicability of different AI techniques to the characteristics of different software engineering problems. And the end result, if successful, is a new generation of tools that help architects and engineers make broad classes of changes to systems with much, much less effort than it takes today, which helps us get the real mission capabilities into the field much more quickly. Thank you.
So on that last one, to get to the end game
At this point, no. So the bottom project is really literally starting this month. So for that project, the tool chain isn't in place yet. We're looking with standard tools like Jenkins and so on that are used in places like Kessel Run. But we're not yet woven that integrated with those sorts of offices. Yes, sir.
I'm just curious, DARPA had a program called Mining Understanding Software Enclaves, which was automation of software, mining the open source code base. Have you explored synergies between this effort and what was the outcome of Muse?
No, not as yet. I think, I think that plays more with the second program, which is really about understanding the semantics of what that code is and what it does. And so that's very much in the formative stages. With the first project, Untangling the Knot, we're really dealing with program structure in terms of a barrier to achieve a specific structural goal.
Question? Yeah. I had a question, more of a funding question. The history I've had with refactoring is nobody wants to pay for it.
Yeah.
And is this addressing that? Maybe indirectly by takes less time, it's quicker, it costs less. Most people don't want to change the software unless they get more functions. And nobody gets excited about changing the software to not be any different from their external perspective.
That has been our experience as well. We hear that story over and over again, particularly talking to engineers who know the structure needs to be improved, who want to get budget and time to go do that, but struggle to do that. It's a similar story you face in managing and mitigating technical debt. So in terms of how this might help, it's unclear, but it's hopeful. So the notion of being able to reduce the effort to 1/3 or possibly less over time, there's a tipping point. There has to be a tipping point somewhere where if the cost to clean up the code base and improve the structure is less than some number, then yeah, I'm willing to do it. But certainly if it's millions and millions of dollars with no capability, no new requirements satisfied, that's a much heavier lift. There are good economic arguments for doing it anyway, but they don't seem to win the day nearly as often as we would expect.
I had another question over here, if you don't mind.
Yes.
So I was wondering if, so as technology progresses into the future, we change, often the language we program in, and I'm wondering if some of the technological challenge between converting from, say, like C# to Python is part of the migration problem, and how you're potentially seeking to address that problem.
Okay, that's an interesting question. So at this point, we're not looking to translate between languages, but I think we're hopeful anyway, that what we learn from strategies that are more effective at improving the structure of one language, certainly gives you a better understanding of what the target in that language should look like. So for example, fitness functions suitable for Python or C#, as a result of these kinds of changes would certainly be fitness functions that make sense when translating to that environment as a target, because it's a measure of goodness.
Any other questions? We'll take one of these.
Oh, okay.
How does your support for refactoring compare to existing refactoring tools?
Okay. So I touched on this just a little bit earlier. So in the IDE space, integrated development environments, tools like Eclipse and Visual Studio and ReSharper provide some basic support for refactoring, but it's really, I probably won't get there quickly enough. It's really at the tail end in terms of making the code changes. Oh, there we go. All right, so this list here at the right. So making the code changes with those tools, you can point an IDE to this is the method that I want to move, and here's the location I want to move it to, and it will go through and make the changes to a number of files to realize that change. So that is helpful, but it doesn't solve the intellectual challenges of figuring out, making those decisions of what to do in the first place. And that's where this work is really sort of filling in a gap that's missing.
All right. I think we're running low on time. There was
All right.
one we didn't get to, but if you submitted the question, please track James down on the break.
All right. Thank you very much.